Okay, good morning. Um, Good morning, everyone. So let's get started. I'm gonna turn off. Hi. All right, I'm gonna turn off my video and let's share my screen here. All right. Okay, so yeah, let's get started. So today we're gonna learn something about the interval mapping for QTL traits, quantitative traits. So as I mentioned, so since we have learned a lot of like very solid, very useful theorem, now we try to apply those knowledge and theorem to different situations. So then we can move much faster than before. All right. So last time we learned how we can. Um, so for example, if we have if we have a project to test the genomic loci and to identify the QTL for a trait. However, if we only have very limited genetic markers along the genome, so those markers cannot represent the whole the entire genome. So what can we do? So what we can do is like if we want to test some uh, genomic locus which are close to a marker, then we can use that marker information, genotype information for that marker to infer that unknown locus given the genetic distance between that locus and the marker, right? So we have learned this before. So today's example, today's topic is relevant to that. Okay, suppose we have a chromosome or genome, so we have very limited marker here. So this place represented the marker, and because we have limited markers, so we cannot. Uh, so these markers cannot represent the entire genome. For example, if we want to test the region in here, so we do not have genetic information, genotype information about this region. So how can we do this? We have learned this before, right? We have learned the 3-point analysis. So what we did in that chapter, so I believe it's about like chapter 3. So given the marker information for A and C, so we call this two markers as the flanking markers. So if we have the genotype data information for these two markers, and we want to infer the genotype for B, so given the distance, genetic distance between A and B and C, then we can do the 3-point analysis to find the probability that uh, uh, that the B locus takes any of the three genotypes. So suppose this is a F2 population, so we know the B can take uh, any one of the three genotypes, right? But if we do not observe the genotype for B, so then we can use the A and C to infer the genotype. Okay, now suppose we knew the genotype data for this marker and this marker, and if we knew the physical or genetic distance between this marker with this locus and the distance between the marker and this locus, so then we can infer the genotype information for this locus, right? And then we can use this information to test whether this locus is associated with the phenotype using a linear model. So this is what we learned before, right? The beta 0 plus beta 1, x1, and so on, something like this. So Okay, now since we can do this, we can test everywhere on the chromosome, on the genome, given the marker information, right? So for example, given this two marker, we can infer this locus, and this locus. So we can test almost everywhere on the genome, and then we can create a smooth, not this. So this is discrete plot, right? We can only test in the first graph. We only test the association between the markers and the phenotypes. So that's not enough. So if we want to do the GWAS, the genome-wide association study, or the QTL mapping along the whole genome, so we need to use some extended knowledge, right? So today we have Dr. Sibo Wang here. So I'm gonna finish this chapter, and after that, probably around like 10:30, I'm gonna give the floor to Dr. Wang. So he will present a example. He will show you how we can use the current tools, the existing tools, to help us do the GWAS analysis. So hopefully that will be helpful in your future research. All right. So okay, now since we can infer the genotype information for any locus on the chromosome, so we can test everywhere on the chromosome and on the genome, in the genome, and then we can create a smooth curve for the test statistic along the genome or chromosome. So for example, here, this is a peak, which means like, there's a strong signal, or a very significant signal indicating the strong association between the locus here and the phenotype of interest. So the GWAS can help us to identify the genomic loci that are responsible for the phenotype of interest. All right, any questions here? Okay, so all right, let's look at this model. So this model is a little bit different from what we saw in the past. So this model is more is closer to the real model we use for the real project. So suppose the YJ, the Y is the phenotype of interest. For example, if we are talking about a rice project, so this Y could be the rice yield, or the heading time, or something like that. All right, suppose we want to find the genomic loci that are responsible for this phenotype. So we can use this model. Of course, this is the error, right? So we assume this error is normally distributed. Okay. And so now we use the first term to represent some non-genetic effect. What is the non-genetic effect? For example, if you want to do a meta-analysis, you want to combine the data from the United States and the data from, let's say, China, the rice data, to combine these two data sets to for a joint study to increase the power. So we believe that the environmental factors cannot be trivial, right? So the environmental so the weather, the temperature, and any other like impacting factors in China could be quite different from those in the United States. So we need to consider that those factors as well. So we use the first term here to represent the non-genetic effects. Yeah, so beta is the coefficient for the non-genetic effects, and X is the design matrix indicating whether this data is from China or from United States. However, yeah, so this term, we put this term here. It's necessary, but we're not interested in this because we actually are interested in here, the gamma. So we use gamma to represent, so everybody should be very comfortable with these two terms right now, right? All right, so we use gamma, which is a vector of length of 2. So we use gamma to represent the coefficients, the parameter for the additive effects and the dominant effects. All right, so this is gamma. Now the z is the random variable that we use to so we can derive from the genotype data from any locus to represent the additive effects and the dominant effects. Okay, so now, so the z is a little bit different. So we can use a H matrix to represent the z variable. So we use a H matrix to represent the z variable. So we're very clear from here, right? So this is like the z. So we used to use z to represent this column. And we used to use w to represent this column, right? So hope you still remember. So the z is associated with the additive effects, and the w is associated with the dominant effects. So if this individual takes the first genotype at this locus, so we're going to use the first row to represent the H1. So the first row, the first element is +1. So that's for the additive effects and 0 for the dominant effects. Is that clear here? So we use H matrix to facilitate our calculation here using the matrix notation. All right. Okay, as I mentioned, because this is the reality. So suppose this is the genome, this is a chromosome. Okay, so this is the first marker, marker 1. And this is the second marker, marker 2. And suppose we want to test this locus. So we use this locus to represent, so we want to test this locus. However, we only knew the genotype information about this marker and this marker, but we don't know here. Suppose this is the real situation for this locus, but unfortunately, we do not know this information, right? So then we can use a u, which is the expected value for z, to replace the real situation z here. All right, so see, look at the difference between these two equations. So they are identical except for this part. So if we knew the genotype data, so we can use z. But if we do not know the z, so we use the expectation of the z to replace it, right? So then the next step is how we can calculate the expected value for the z. So which is u, right? So we knew the technology. We learned this technology before. So okay, so how do we calculate the expected value for z? So we can use the information from the first marker and the second marker to calculate the probability that this locus takes the first genotype. So this is the probability, and for the first genotype, and this is the probability for the second genotype, and this is the probability for the third genotype, right? So we use this weighted summation to represent the expected value for the unknown variable, genotype variable z for this locus. Any questions so far? Okay. All right. So now suppose we can successfully calculate this u, right? So remember what the u means, right? U is actually the expectation of the unknown genotype variable for this locus, all right? So suppose we can calculate this. then the business becomes much easier, right? We have learned this routine. So if we have this information, we can use the least square or MLE to get the clear solution for the parameters here. So here, the gamma represents the genetic effects, including the additive effects and the dominant effects. And we can use this least square estimation to calculate this, to estimate this these parameters. And also we can, once we have this estimation for the beta and the gamma, so we can estimate the variance for the residual error. And then that's easy. So we can calculate the variance of this estimation, right? And once we got this, so we can, okay, so this is the thing we are interested in, because here we are not, so we don't worry about the environmental factors, the non-genetic part. We are only interested in the genetic part. So we can take this part out here, and this is the variance of the estimation for the additive effects and the dominant effects. And once we got this, so we can easily construct a test to test the additive effects and the dominant effects to see if any genetic effects, either the additive or the dominant, exist at this locus, right? So then we finish the test for this. So this is marker 1. This is marker 2. And so we tested this one. So this gives us a statistic like this high. And if we test this locus, so maybe we got a better statistic, and this locus dropped a little bit, and this one dropped, this one dropped, this one dropped, and this one dropped. So there's a peak actually here, and this indicates the high peak in the statistic curve indicate a strong association between this locus and the phenotype of interest. Okay, we have learned, so we can use the word test to test whether this locus is associated with the phenotype or not, or we can use the likelihood ratio test, right? The likelihood ratio test. So the likelihood ratio test is to compare two likelihood. The first likelihood, the non-likelihood, is the likelihood based on the non-hypothesis. And the alternative likelihood is the likelihood that is based on the alternative distribution. So the non-distribution means like we assume A equals to 0, additive effects equals to 0, and D equals to 0, right? And in the alternative distribution, so we can use the estimated A and estimated D to generate the likelihood function. And then we can compare, sorry. So then we can compare the ratio of the likelihood. Actually here is the difference between the log likelihood, and then this is a chi-square distribution. So we can use this to find the p-value, and the p-value can be used to generate a lot score, which can help us to create a continuous smoothie curve for the test statistic along the chromosome or genome. So is it clear? Is it clear? Okay.
Yeah, so far.
Very good. Very good. Thanks. Okay. Yeah. So yeah, this is a funny cartoon. So here we want to compare the non-distribution with the alternative distribution. So of course there's difference, right? So if we can compare the ratio, likelihood ratio of these two, so we can test which one fits your data better. So this is how we do the likelihood ratio test here, likelihood ratio test. All right. All right. So now this is a new method developed by Dr. Xu in 1998. This is an extended model that can be used to do the interval mapping, quantitative interval mapping for the quantitative traits. So now we are very clear about this, right? So this is the model we use: phenotype, the non-genetic effects, and the genetic effects. And here, our gamma actually includes additive effect and a dominant effect. All right. So okay. So suppose this is the reality. So this is the reality. However, we do not know the genotype information at this locus. So we use a expectation of the Z in the model. So then let's see what happened. Because this is the reality. So this is the reality. If we use an expectation to replace this, this will introduce some error, because even it is an expectation of Z, so it is not identical to the real Z, right? So the difference between the real Z, which is unknown, and the expectation of the Z, that's the part which introduced additional error to this model. Okay, so look at the difference between this model and this model. Let me clean this first. If you compare this two and this one and this one, they are actually the same. We just plus and minus this term in the model, so they are identical. However, using this model, this equation, we can clearly see that because in the real calculation, we use the expected value for Z rather than Z itself. And this is the error, additional error introduced by using the U, right? The expected value for the Z. All right, and this error, the newly introduced error, will be lumped into the random error to form the combined error. So this is the real error term in the real analysis when we use when we use the expected value of the Z rather than Z itself. Is that clear? Is that clear? Okay, so this is the model we use for the real data analysis, because in the real data analysis, we use the expected value of Z in the calculation. And this error actually includes two parts: the, the, the original random error and the error introduced by using the expected value of Z. So this is the real error term in the data analysis. Okay, now let's look at here. So the expectation of the real error is also equal to 0. That's no problem. But the variance of this is no longer a simple normal distribution. So if you look at the variance of the real error term, so it follows a equation like this. So this is the normal distribution, but we have an extra term here because of the introduced error here, right? Any questions here? Okay. All right. So now, okay. So this is the equation. This is the equation we are using now, and because this is a linear model, right? We can use the MLE or least square to help us to estimate this. So this is the major step. So we want to use the data to estimate this guy, gamma. Gamma includes additive and a dominance effect. All right. So, okay. Now, because when we use the least square or MLE, so we have to calculate this, right? Because this is the variance we need to calculate. All right. So the sigma actually, the variance of this is, so we can calculate the expectation of this minus this, right? This is how we calculate the variance. So I hope you still remember how we calculate the formula for calculate the variance for a random variable. And okay, so the expectation of this part, so this part is actually, so we can use this to calculate this part. And for this part, we can use this equation to calculate this part, right? Okay, now once we calculated this and this, so this is solved, and we can express, so the previous slide is here, right? So this is what we got here. And so we can express the variance for the real error into this. And if we let this, oh, sorry. Ooh, it's not good. Sorry about this. So if we let this equal to W, so let W equals to this, then we can express this thing using this. We call this Wj as a weight. So that's why this method is named as the weighted least square. So we use a weight here. Okay, now then we can solve we can get the solution for the parameters, right? So here we want to, this is what we want. So we want to get the solution, the MLE or the least square for the gamma. So this is the solution. However, if you look at this equation here, so there's a problem. There's a problem because when we want to calculate, so when we want to calculate the real variance for the real residual error, so if we want to calculate this, we must know the weight, right? Okay, but when we want to calculate the weight, we must know the sigma square. So this is a problem because these two things are entangled with each other. So which means in mathematics, which means there's no solution. There's no unique solution for these equations because one equation involves two unknown variables. So in mathematics, yeah, so you cannot get a unique solution for this. But fortunately, so we use statistics analysis, so we can use the iteration to help us get the solution for both of them. All right. So okay, because this weight, the Wj weight and the sigma square, yeah, because one is the function of another one. So mathematically we cannot get the unique solution, but in statistics, when we use the iteration, we can get the solution for them. So we have learned this before, right? So we use the iteration. What we do is like we can give the program, we can let R or other statistical program to know the initialized value for gamma and the sigma square. Once we have the realized the initial value, we can calculate Wj. We update it. We can update that Wj, right? Once we get the updated value for Wj, we can then use this updated value to go back to estimate, to calculate the sigma square and update the sigma square using this value. Then we do the iteration, and once the iteration converge, then you have the solution for both of them. Is that clear? Any questions?
Is this a similar pattern to the EM algorithm?
Yes, very similar to that. Because so yes, very good. So we can assume this. So this is the MLE. So for example, this equation shows we can treat this is the MLE for the W, right? but because when we, so if we knew everything in the right side of the equation, then this is the MLE for this guy. However, we do not know this thing on the right-hand side of the equation. What we do is like we use the expected value for this to replace it, right? So that's the E step. So the E step, we use the E step to update this. And then once this thing is realized or updated, we can use the whole thing to get the MLE for this. So this is the EM algorithm. The same thing here. So because this is the MLE for this guy, but when you look at the right-hand side of the equation, this involves the unknown value, right? So what we do is like we use the expected value W to replace this guy, and then we get the MLE for this. So because this is beautiful setting, so we can use the EM algorithm to solve this problem. Yeah. Any other questions? Good. Okay, so okay, once the program converges, so we get the solution for beta and the gamma, right? And then we can immediately get the variance of these two of the parameters as well. Okay, then wow, we are almost done. So we got the estimation for the additive and the dominant effect, and we can also calculate the variance of this estimation. And then this is what we are very familiar with now, right? So we can either use this estimation to calculate the likelihood for the alternative model, and we can also calculate the likelihood for the non model, the non-hypothesis, and then we can construct a likelihood ratio test, which is a chi-square distribution, and this can help us to do the testing for this locus, right? Okay. And also we can use the Fisher score, because remember, so this is not a complete data problem. This is a missing data problem because we do not observe the genotype data, the genotype for the locus of interest under the test. So this involves a mixture model. So we have learned a mixture model, right? And then, so we cannot just use, but we have showed that even this is a mixture model, so we can still prove that the MLE is equivalent to the MLE in EM algorithm. So we have shown this before, right? So then we can use the Fisher score to help us to calculate the variance of the estimation of the parameters. Okay. So this is the equation. I just showed you how we can use this weight to calculate the real error for the model, right? And we can use this to construct the likelihood function, and then we can do the log likelihood function like this. So this is what we have done before, and so we can do the first derivative and the second derivative, and we got the information for the parameters. And once we got this the information, the Fisher's information for this estimated parameters by the iteration. So we use the EM algorithm, something very similar to the EM algorithm. We use the iteration to get the solution for the parameters. So we are actually interested in gamma, right? Gamma include additive and the dominant, and then we can get the Fisher's information for this estimation, which is equivalent to the variance of this. And then once we got this, the variance of this estimation, so this is also the business we're very familiar with, right? So we can construct a mixture model here. So this is the mixture model because we do not observe the genotype for this locus. So we can put the density function for one single observation into a by using a summation of the three of the density functions here, right? This is the mixture, and then we can get the MLE for this estimation, and also the variance of this estimation. This is the mixture. So any questions about this mixture model here? So we move, you can see we move very fast, right? So by assuming that we are very comfortable with the stuff we have learned before. Any questions about here? So this is how we use the E step, the expectation step, to calculate the probability. So given the parameter estimated in the M step, so we can calculate the density function for each of the three mixture normal distribution, right? And then by using this model, we can calculate the expected value for the P. So what is this? Can anyone let me know what's the meaning for this guy? Oops. So what is the meaning for this guy? Look at the numerator here and the denominator. So how do we explain this formula? Can anyone help me to understand this? This is the E step.
This is a probability for that three genotype.
Yes, yes. So because we want to calculate this, right? That for this individual, so what's the probability that this individual takes the first genotype? What's the probability that this individual takes the second genotype? And first, what's the probability that this individual takes the third genotype? So we have three things to calculate. Suppose we want to calculate Pj plus 1. This represents the first genotype, right? So we want to calculate something like the weighted probability for the first genotype. This is the numerator, and in the denominator, we just add up three the weighted probabilities for the three categories. So this is equivalent to this thing. So in shorthand, so let's say P plus 1, J, this is the numerator, and the denominator should be Pj plus 1 plus density function, of course, y times density function here, y plus Pj 0 plus times the density function, right? And plus Pj minus 1 times the density function. Is that clear? So we use this to calculate the expected value for each of this. Once we got this, so we can migrate to the maximum maximization step to use the MLE to get the clear, the closed form of the solutions for the parameters of interest. Any questions on this slide? Okay. All right, so the EM algorithm. So here we just follow the routine. Okay, so we initialize the parameters at the time 0, and then we just alternate the E step and the M step iteratively until the whole process converges to a point, suppose here, and then we get the solution for the parameter, and we also can calculate the variance of these parameters. Then we can do the test. So by this way, we're done with one locus, right? We do the same thing for the whole genome to generate something like this. This is the loss score, for example. And okay, so we can set up a cutoff. Of course, we're gonna consider the multiple comparison here, right? So I hope you still remember. So we have a lot of ways to control, to test the significance level to make sure we can have enough power, or we can reduce the false positive cores here. So for example, this is the Manhattan plot. At this genomic locus, so we got a very strong signal, and this will indicate the strong association between this locus and the phenotype of interest. Okay, any questions here? Very good. All right. Okay, so this is the information matrix. So once your algorithm converge, we can get the information, and by using the inverse of the features information, we can get the variance of the estimation for the parameters, and then so we can do either of the either test, right? Either we can use the Ward test to test gamma. So gamma here is the genetic effects, or we can construct a likelihood ratio test to test the genetic effects. So by using either way, so you can generate a beautiful Manhattan plot like this, something like this. So Dr. Wang will show you how he can use the different advanced statistical program to generate the Manhattan plot to help us to identify the genomic loci that are significantly associated with the traits of interest. Okay, so this is example. Okay, so for example, I believe this is still the same example using the mice data. So this is a F2 mice population, and the x-axis represent the entire genome, about like this long, Sandy Morgan, and so the dashed line here actually separate the different chromosomes. So for example, this region is the first chromosome, this region is the second, the third, and so on. Okay, now we have, I hope you still remember, along this 19 chromosomes, we only have like 193 markers. So if we just test the 193 markers, we can only get the discrete test statistic. However, by doing the interval mapping, if we use the information about this 193 markers, we can infer the genotype of any locus on the genome, and then we can produce a continuous the smooth curve about the test statistic along the entire genome. All right. Okay. So this is the test statistics along the genome, and this is the cutoff, the threshold that we're going to use for detecting the significantly associated loci. So for example, these two loci in this analysis, GWAS analysis, these two loci are significantly associated with the traits of interest. All right, so here we use the loss score as the test statistic for the GWAS analysis. Okay, so this plot shows the test statistic, and this plot shows the genetic effects. So remember, doing this test, we can also estimate the magnitude of the genetic effects, either the additive effects or the dominant effects. And once we get the estimation for that, we can plot that effects. For example, if this is the additive effects, we can plot the effects along the genome to see what's the magnitude of these effects. So I believe this is the region we found to be significantly associated with the traits. And if you look at here, the effects, the genetic effects are also large at these two loci. So this is the results basically you can generate from your GWAS analysis. Okay, so I think I'm done with this chapter. So I'm gonna, so if you have questions, we can discuss for a short time before we let Dr. Wang to present his GWAS study. Any questions?
Yeah, I have a question, Professor.
Yeah, sure, Livy.
So in this graph that you're showing, what do we infer if the lines are below the threshold, and what if it's above? Like, is it a negative effect or?
Oh, yes. Okay. Yeah, good question. So to answer your question first, let's talk about this graph first, okay? So these two graphs are actually corresponding to each other. So this is the graph showing the test statistic because we are using the log score. So this log score is a non-negative. So that's why you always see the graph above the 0, right? Okay, so that, however, so the larger this log score, the smaller the p-value. I hope you still remember. So for example, this 2 peak probably represent the p-value equals to probably like 10 to the minus 6 or something. So because we test each locus using this p-value or log score, right? So this small p-value shows the non-hypothesis is not true. Now we're gonna reject the non-hypothesis and say these two loci are significantly associated with the traits of interest, right? Okay, so this is the log score, the test statistic graph. We call this the Manhattan plot. All right, now look at here. So if we can put these two graphs together, you're gonna see they are corresponding to each other. Okay, now this graph shows the estimated additive effects. Okay, so for example here, this is a negative thing, right? Which means, okay, so if you define A1 as the first genotype, A1, A2, the second, and A2, the third, all right? And if you define A as the A1 minus the midpoint, A1 plus A2. Do you still remember this definition? Okay, now this will be negative, means like, so this totally depends on how you define the genotypes, right? So if you define the A equals to the difference between the A1 and the midpoint, this estimation will give you a negative estimation at this locus. What does that mean? That means like, all right, so this is your A1, and this is your A2. And if you link this two, this is the midpoint, mu, and probably your A1, A2 is here. Oops, it's not very clear. Let me draw another plot here. So this is A1, A1. This is A2, A2. And here, probably, this is mu. This is A1, A2. Is that clear? So yeah, this represents this negative effects. But the positive effects is something like we are very used to that, because usually we assume like A1 has a larger, greater phenotypic value than the A2, right? But if you look at here, so this negative things means like when you define A1 as A1 at this locus, the A1 actually is associated with lower phenotypic value than the A2. Mm-hmm. Does that make sense?
Yep.
Okay. So any other questions?
Yes.
Yes,
So
right. Yeah.
positive effects are sometimes they can be a little bit large sometimes because especially if they're dominant.
Yes.
So,
that's right.
that is expected. Is there any way to compensate this with putting the dominance effect into consideration?
Yes.
Okay, we're just not talking about it now. Okay,
Yeah.
that's fine.
Yeah. That's right. Yes. Because yeah. So good question. So this could be a additive effects plot, and it could be a dominant effect plot. So you can generate another plot like this for the dominant for D. So this will also give you something like this, and this will. So if this is a dominant effect plot, so from this plot you can tell. So you can learn something about a specific locus in that place, whether the dominance will give you either the additional increment of the phenotypic value, or you will if you will see that the heterozygous will give you additional reduction in the phenotypic value, something like that. So based on the negative or the positive values.
Got it.
Mm-hmm. Good, very good question. So just now I just assume this is an additive effect plot, but yeah, you can treat this as a dominant as well. So maybe so in the real example, when you plot the additive effects and the dominant effects and put the two plots side by side, these two plots could be quite different. So could be quite different. Yeah. Does that make sense?
Yes.
Okay. Good. Any other questions? All right. So if you do not have questions, I'm going to give the floor to Shibo. So Dr. Wang, yeah, please.
Thanks, Dr. Zhang.
Mm-hmm. So I think because Dr. Wang is using his the desktop without any camera, so unfortunately we cannot see his face, but yeah, we can hear his voice and the PowerPoint slides. Okay, please.
Hi everyone. Today I will introduce the widely used tools for genome-wide association studies. My presentation includes two parts: peeling formats and the GWAS tools. Peeling formats are widely used in the GWAS analysis. Today I will briefly introduce three formats. First, the PIDE and MAP format. It contains two types of files, PIDE and MAP. The PIDE file contains sample information, and the MAP file includes the SNP information. In the PIDE file, each row represents one individual. The first 6 columns correspond to family ID, individual ID, parental ID, maternal ID, sex, and phenotype. From the 7th column, the PAD file stores the genotype data. All markers should be biallelic. For example, like this one. All SNPs has 2 alleles specified. Missing values are coded as 0. In the map file, the first column represents chromosome SNP ID, genetic distance. If we do not know genetic distance, we can code it as 0. For example, like the 0 in this picture. And the fourth column represents the base pair position. Another format is the 5-bin byte. It's also called the P-link binary format. The PAD and MAP files above can be converted to files of this format using the code below. Test is the name of the input PAD and MAP files, and test3 is the name of the converted output P-link binary files, 5-bin byte files. In this picture, the first 6 columns of the 5 files are the same as the first 6 columns of the PAD file. For example, like this picture in the slides. The first one, family ID, the second, individual ID, the third, paternal ID, the fifth, maternal ID, and the fifth, the sex, and the sixth, phenotype. Also, the first 4 columns of the bin file are the same as those in the map file above. In each row, the last 2 columns of this bin file represent 2 alleles for the corresponding SNP, like this one in the picture. Each row represents one individual in the byte file. Unlike the FIME and bin files, the byte file cannot be readable using the usually used tools like Notepad and Excel. Usually, FIME bin byte are converted from P-link files of other formats. The TPAD and TFIME files can be converted from the PAD and MAP files using the code below. Each row in the TFIME files represent one individual. The first 6 columns of the TFIME files and the PAD files are the same. For example, this is a sample of the PAD file. The first 4 columns are the same with the first 6 columns of the TFIME files. Each row in the TPAD files represent one SNP. Like this one, the first SNP. The first row represents the first SNP. The first 4 columns of the TPAD files are the same as those of my file. From the fifth column, the TPID file stores the genotypic data. All SNPs have two alleles specified. Secondly, I will introduce three widely used GWAS method based on the published data. IMRX, FASTA, LMM, and GMR. IMRX was proposed by Kang in Nature Genetics in 2010. IMRX can improve computational efficiency when analyze large GWAS data compared with IMR. Also, IMRX estimates various components of their ratio only once and then fix them to test all the genetic markers. That's why IMRX is faster than IMR. IMRX support TPID and T5 p-link format. Users can use p-link with the code below to generate the input files. The record 1, 2 marks by the red color is necessary for the format conversion. Parts of the content from the converted TPID files is shown in this slide. The two alleles for each SNP are coded using 1 and 2 instead of ATCG. IMRX has a function of calculating the kinship matrix. The software provides two ways of calculating kinship, that is IBS and BN. The code below represents to the two different kinship matrix calculation. This is IBS matrix and this is BN matrix. This slide shows the example of an IBS kinship matrix of a 10 individual sample calculated by IMRX. This one, the element from the second row, the first column reflects the relationship between the first and the second individuals. In IMRX, the phenotypic information was stored in separate files for input. The three columns represent family ID, individual ID, and phenotype. The missing phenotypic values are coded as NA. For IMRX, it can also add covariance in a separate input file. The first column are also family ID and individual ID. The third column corresponds to the intercept, meaning that the third column is recommended to be 1 always. The covariance needs to be included from the fourth column. The code for the GWAS in IMRX are listed above. -T follows the name of the input genotypic data file. -P follows the name of the input phenotypic data file. -K follows the name of the input kinship matrix file. And -T follows the name of the input covariance data file. minus O follows the name of the output result file. The results sample is shown in this slide. In each row, the first and last column represents the SMP ID and the p-value from the significance test. Secondly, I will introduce another GWAS method that is FastLMM. FastLMM was proposed by Leppert in Nature Genetics in 2011. FastLMM can handle large sample size data. Also, FastLMM is time-saving and memory-saving compared with MRX. FastLMM supports multiple p-link format for genomic data input, like FINE-BIND, p-link binary format, MAP and PAD, TPAD and TFINE. Also, the phenotypic data is stored in a separate file. In each row, the elements represent the family ID, individual ID, and the phenotypic value for one individual. The missing values are denoted by -9. The first two columns are the same as those in the covariant file. From the third column, it stores the covariance. The code for GWAS in FastLMM are listed above. For example, -T file follows the name of the input genotypic data file of TPAD and TFINE format. -T file sim follows the name of the input genotypic data file for calculating the kinship matrix. And -pheno follows the name of the input phenotype file. -cover follows the name of the input covariance data file. And -m file follows the index for the phenotype to process. For example, it can follow first, means we analyze the first phenotype in the phenotype. -out follows the name of the output result file. This slide shows the result sample. The fifth column represents the p-value from the significance test of the SNPs. Lastly, I will introduce the GAMMA. GAMMA was proposed by Zhou in Nature Genetics in 2012. GAMMA is a method for exact calculations compared with MRX. And GAMMA is more efficient method than MRX and FastLMM. Also, the results of GAMMA are numerically identical to EMMA. GAMMA supports p-link binary files, FINE-BIND and BIM. It also supports files of BIM-BAM format. BIM-BAM format accommodate any real values from 0 to 2. Also, it can analyze non-genotypic data using the not SMP option. The code for GWAS in GMR are listed above. -B file follows the name of the input genotypic data and the phenotypic data file. -miss follows the threshold for missing list. For example, SMP with missing list below the 0.01 will removed from the GWAS analyze. -LM follows the option specified which significance test to use. For example, this one performs Warden test, and this one performs the likelihood ratio test, and the third one performs the score test. Usually, I use the last one perform all the 3 tests above. -MAF means SMP with a minor allele frequency below this threshold will removed from the GWAS analyze. And -O follows the name of the output result file. This slide shows the sample result file. This one is SMP ID, and this one, the third column, is a base pair position on the chromosome. And this column represents the minor allele, and this one represents the major allele. The AF represents the allele frequency, and this one is a p-value from the Warden test. The last slide shows a Manhattan plot of the GWAS result. Usually, when we have done the GWAS analysis, we will generate an Manhattan plot. The plot shows on the y-axis the negative log-based 10 of the p-values for each of the SMP in the genome. And the plot shows on the x-axis shows the base paired position for each of the SMP in the genome. Usually, we use the Banff-Rawney correction, perform each test at level of this value. For example, in this picture, the dashed line marks the threshold of the GWAS analyze, and the point above this line, we treated them as a significant SMP associated with the corresponding trait. Thanks everyone.
Thank you, Sibo.
Thank you, Dr. Jia.
Yeah, sure. So any questions for Sibo? Yeah, it's very, very nice presentation. And so I wonder if you have any questions for Sibo now. All right, so in this class, actually, we learned a lot of fundamental basic knowledge about the test. Actually, those are important part. So once you understand the underlying theorem, so it's good for you. So in the future, when you use any of this GWAS method that Sibo have shown. So once you use this to analyze your data, so get when you get a very nice, beautiful results and plot Manhattan plot from this program, so you understand what is exactly going on behind this program, and so not only get the results, but also you can explain these results to your colleagues in the future when you go to some scientific conference to present your data. So I think, yeah, this is why this class is useful and helpful. So any questions so far for Sibo or for the interval mapping of the quantitative traits for today's class? All right, very good. So if you do not have any questions for now, so we will dismiss the class for now. And this afternoon we have a office hour. So so if you have questions, bring your questions to my office hour. Or if you have, so if you cannot come, so just let me know, either by email, email me with your question. I try to answer your question through email, or if you prefer like the talk like this to discuss your question, you can you can schedule another time, either this week or next week, so we can talk about your questions. All right. So so if you do not have any questions, so we're gonna dismiss the class for now. Okay. Thank you, Sibo, and thank you, everyone. See you. Bye-bye.